Hello everyone, I hope you're all healthy and doing well. In today's lecture, we're going to cover section 5.5, the fundamental theorem of calculus. If you remember what we did in the previous two videos, we first defined the definite integral of a function, a continuous function, over a closed and bounded interval using upper and lower Riemann sums. And then we investigated some basic properties of a definite integral. The problem with our definition is that conceptually there's no problem with our definition. Like it does what it's supposed to do perfectly. It gives you the signed area under the graph of a function over an interval and so on. But the problem is, like, for practical purposes, if you want to compute definite integrals, when I give you a function, unless that function is very simple and basic, it's going to be very difficult for you to compute the upper and lower Riemann sums for an arbitrary partition. I mean, you can write the sum down in sigma notation, but you won't be able to find a closed form easily most of the time. And that's going to result in you not being able to find the limit of these upper and lower Riemann sums. So the point is, it's difficult to compute the definite integral using the definition. So we have to do something else. Today, when we finish learning about the fundamental of calculus, we will also have learned the proper way of computing definite integrals using antiderivatives. Now, I use the phrase that we haven't used before, antiderivative. So let's start with that, because in order for me to state the fundamental term of calculus, I have to talk about antiderivatives, okay? So we'll start with antiderivatives. Antiderivatives. Okay. A function big F of x is called an antiderivative for little f of x on the interval I if the derivative of big F of x is equal to small f of x for all x in the interval I. Okay, in I. So I'm assuming that here I is an open interval, where I is an open interval. So big F being an antiderivative of a small f simply means that the derivative of big F has small f. Okay, I mean the name suggests what it's supposed to do. You have two functions. If when you differentiate this, when you take the derivative of this, you get this one. This is supposed to be the antiderivative. Like anti-differentiation is, by definition, is the opposite of differentiation. It's the reverse operation. Okay, so we have antiderivatives. Now, you might have realized that I didn't use the article the, I said an antiderivative. I didn't say the antiderivative. And there's a reason for that. Given two functions, big F and big G, we have that these functions are antiderivatives of the same function if and only if these functions differ by a constant for some constant c on each interval a in their domain. Okay, so as I said, I said an antiderivative instead of the antiderivative. So why did I do that? Because a function can have multiple antiderivatives. Indeed, a function always has infinitely many antiderivatives, and there's a relationship between these antiderivatives. Take two functions. I claim that these functions are antiderivatives of the same function if and only if the difference of these functions is a constant on each interval in their domain. Okay, so I'm saying that given a function, two antiderivatives always differ by a constant and vice versa. And why is this true? Let's think about this. I'm saying A if and only if B. That means that if A happens, then B happens, and if B happens, then A happens. Why is this true? The left-right direction is easy. If you assume that these functions are the antiderivatives of the same function, then, well, okay, this is the non-trivial direction. Actually, we're going to use Mimel theorem. The other direction is very easy. So let me explain the other direction first. Let's go in this direction. If you assume that two functions differ by a constant, then when you take the derivative of both sides, you're going to get f prime minus g prime equals 0. So you're going to get f prime equals g prime, which means that f and g are antiderivatives of the same function. So it's easy to go from right to left. If two functions differ by a constant, then they are antiderivatives of the same function. Why is the other direction true? Because, let me explain it. I'm not going to write it down. Pretend that f and g are antiderivatives of the same function. You want to say that they differ by a constant. If they did not differ by a constant, then this function would be non-constant. Let's call this little h, okay? Pretend that these functions did not differ by a constant, then this would not be a constant function. If it's not a constant function, it takes two different values, like that, or maybe like that. In any case, if these are differentiable functions, h is differentiable, and by mean value theorem, you would be able to find a point where the derivative of this thing is different than 0. But if these are antiderivatives of the same function, then their derivatives differ by that their derivatives are the same. So the derivative of this h should be 0. So if I assume that f and g are antiderivatives of the same function, then this h has 0 derivative. But if you have 0 derivative, you have to be a constant function by mean value theorem, okay? Otherwise, you can always find, like, if you can take two distinct values, you can find a point where the derivative is non-zero. Clearly, like, this happens, in order for me to say that, I need to assume that these functions are differentiable. So let me write that down. Given differentiable functions, blah, blah. So we have that. Now, that means that when I have an antiderivative of a function, if I add a constant to that, that will still be an antiderivative of the same function. Okay? So, why don't I, given a function, okay, pretend that given a function I found an antiderivative, I add a constant, it is still an antiderivative, I add a constant, it's still an antiderivative. Why don't I just take all these functions together and give that a name, okay? So, given a function f, we will define the indefinite integral of f as the class of all antiderivatives of a f on the domain of f and denote this by where big F is an antiderivative of a small f on the domain of f. Okay, so this definition is a bit different than your book's definition, but not that different. So your book merely uses this as a notation, your book merely uses this as a notation. I'm going to define this as the set of all antiderivatives of little f. Okay, so I'm just going to define this as a class of functions. I think this makes more sense. So what I'm doing here is this. I have a function little f. I'm defining its indefinite integral to be not just a single function, but a set of functions. A set of functions doing what? A set of functions which are exactly the antiderivatives of a little f. Okay, so this is not a single function, but it's a class of functions, and it's the class of functions consisting of all antiderivatives of f. Okay, so in this thing, I have all the antiderivatives of f. So let's pick an antiderivative, big F. I know that all the other antiderivatives differ by a constant from this one, by the previous observation. So I'm just going to write this equals f of x plus c, okay? So you can think of this equality as a notation as well. When I write this equality down, that means that this is simply an antiderivative of this function. This big F is an antiderivative of this one. Or you can also interpret like this. This is the set of functions which are of this form. You get a big F, and then you just add a constants to these, to this function to get all the other antiderivatives. But you have to be careful about some minor points, which I should mention. Okay. Before that, I should explain something. So at this point, you might ask me the following question: why are we using the integral sign? Why are we using the same notation? I mean, the definite integral has nothing to do with this. It has something to do with Riemann sums, whereas this is about the anti-differentiation. So why are we using this symbol? This is going to become clear when we learn about the fundamental theorem of calculus. Okay. So for now, just go along with this, okay? So, a couple points. When we write this, it means that any antiderivative of little f differs from big F by a constant on each interval that makes up the domain of f. Okay, this is a minor point which is not mentioned in many calculus books, so I'm just going to mention it because, well, it's not going to create any problems for you, but if you're going to learn things, learn them properly, okay? Like in general. Not this is that's suggestion was not just about mathematics. So here's the thing. Let's say that let me write down an equality minus 1 over x squared dx. Okay. So you're going to say that this is 1 over x plus c. Okay. And people, like when I write this down, people say that, okay, that simply means that like any antiderivative of this is of the form 1 over x plus c. That's not completely correct. It's almost correct. Okay. So when I write this, that means that the antiderivative of this function will be of the form 1 over x plus c for every interval that makes up the domain of your function. In general, there will be only like you only see one piece, one connected interval which makes up the domain of your function, but there can be more. And what can happen is this. Think of, consider this function, big f of x. It's of the form 1 over x plus 1 if x is positive, and it's 1 over x minus 7 if x is negative. Now, the derivative of big F is still 1 over x, but big F is not of the form 1 over x plus c, okay? Because for positive x, for positive x, the c is 1, but for negative x, it's minus 7, okay? So it's not exactly in that form. It's in that form on each connected a piece of your domain, okay? So I'm just going to put it here. So this is what I mean by like an antiderivative of f differs from f by a constant on each interval that makes up blah blah blah. You see over here that my domain consists of two open intervals, and on each interval this function big F looks like 1 over x. They differ by a constant, but on each different interval that constant might be different, okay? So that's that. Now let me list some basic indefinite integrals, okay? Some basic indefinite integrals. So the indefinite integral of x to the power p will be x to the power p plus 1 divided by p plus 1 plus c for p other than a minus 1, okay? So if p is not minus 1, the indefinite integral of x to the power p is x to the power p plus 1 divided by p plus 1. If p is minus 1, then you have 1 over x here. And then the indefinite integral of 1 over x is ln absolute value of x plus c. But when I write plus c, like again, the domain of this function ln of absolute value of x, it has like two pieces, two connected pieces, the positive numbers and negative numbers. When I write this down, that means that an antiderivative of this function is of the form ln of absolute value of x plus something for positive numbers and ln of absolute value of x plus something for negative numbers. So I have that. So that's that. Let me list some more indefinite integrals. The indefinite integral of sine s minus cosine. Why? Because if you differentiate minus cosine, you're going to get sine, okay? Because the derivative of cosine is minus sine. And if you take the indefinite integral of cosine, you're going to get sine, okay? And then, let me do this. Let's take the integral of a secant squared. This is what? This is tangent x plus c, because like how can you check the such an inequality? How can you like in general, how do you prove such an equality? You're supposed to differentiate big F and you're supposed to get little f, okay? So when you differentiate tangent, you're going to get secant squared, so that's that. The indefinite integral of secant tangent is secant x plus c. Okay. What else should I list? Okay. Let's involve the inverse trig functions. The derivative of sorry, did I say derivative? Yes. The indefinite integral of 1 over square root 1 minus x squared is arc sine of x plus c. And let's see. The indefinite integral of 1 over 1 plus x squared is arctangent of x plus c, and so on. I mean, I can just list more. We learned about derivatives, so for every derivative that you can find, I can write down the corresponding equality involving indefinite integrals, so I'm not going to do that. So that's that. And I think it's enough that I talked about antiderivatives. Let's now talk about let's talk about the fundamental theorem of calculus. Now, the fundamental theorem of calculus, well, look at the name, the fundamental theorem of calculus. So it's unarguably the most important theorem that you're going to learn in this course because it is the fundamental theorem, and you will just keep using this over and over again without explicitly writing most of the time. So, what does the fundamental theorem of calculus Okay, I think I'm going to turn on lights. I'm sorry for this. What does the fundamental theorem of calculus say? The fundamental theorem of calculus has two parts. The part that you're going to be using to compute definite integrals is the second part. But the first part is just as important, and indeed we're going to use the first part to prove the second part, okay? Now, the first part of fundamental theorem of calculus tells you the following. Okay, let me first write down my settings. So let f be a continuous function on an interval I containing the point A. Okay? So the first part of part one of fundamental theorem of calculus tells you the following. Then the function big f of x defined by this rule is differentiable on I, and moreover the derivative of this function with respect to x is little f, okay? And the second part tells you that for any b and I, we have that the definite integral of little f from a to b is equal to f of b minus, well, I shouldn't really use big F. I should use big G of b minus big G of a for any antiderivative big G of f over the interval AB. Let's say I over I. Okay, that's better. Now, let's understand the statements. First, I set up I set up the framework. I have a continuous function on an interval, okay? We're going to talk about why we need continuity after we prove this. I have a continuous function on an interval, and I fix a point. So I have my interval, and I have my continuous function. I define the following function. Okay, I'm not going to tell you the definition first. Let's talk about how we define function. How do you define a function? For each input, just tell me how to compute the, well, in general, roughly, like how do you define functions in general? I give you an input, you should tell me how to compute an output for that input, yes? I give you an input x, then what you're going to do is, in order to compute the output, you're going to compute the definite integral of little f on the interval ax. So you're going to do this for every x. So you're going to change your x, and then you're going to get a different number. So for each x, you're going to compute these numbers, compute these definite integrals, and you're going to consider the corresponding function. The function, which I named here big F, which is the definite integral of little f from a to x for every x, okay, in this interval. And x can be on the left, it doesn't matter, okay? You define this function. The first part of fundamental theorem of calculus tells you that this function is actually a differentiable function. It's differentiable on I. And not only is it a differentiable on I, it's actually an antiderivative for little f, meaning that its derivative is little f. Okay? So this is the first part of the fundamental theorem of calculus. So, fundamental theorem of calculus, first part tells you the following. Take a continuous function, fix a point. My point A is fixed here. For each x, consider the function f, which is defined as follows. F of x is the definite integral of a little f from a to x, okay, which exists because it's a continuous function. Then this big function big F, it's an antiderivative for a little f, okay. So we have that. Now the second part of fundamental theorem of calculus tells you the following. The definite integral of little f from a to b can be computed as g of b minus g of a, where g is any antiderivative. Okay? So the second part now tells us that in order to compute a definite integral, you don't have to deal with Riemann sums. Grab any antiderivative, plug in these endpoints, subtract. Okay? Now let's prove this. I'm going to prove this because the proof is actually important, I believe, and we learned all the necessary tools to prove this. So how do you show that a derivative of something is something else? Let me just write down the definition of derivative, okay? By definition of derivative, by definition, we have that the derivative of this function is f of x plus h minus f of x divided by h goes to 0. And let me explicitly write this down. Using the definition of big F, you just write this as a integral of a little f from a to x plus h minus integral of little f from a to x, and you divide this by h. Now, you can actually rewrite this as by using the properties of definite integral that we learned. You can rewrite it like this, okay? And then another property that we learned tells you that this has to be then the same as this has to be, okay, this is x clearly, because I'm basically what I'm doing is I'm flipping the upper and lower bounds of a definite integral, so it's going to get a minus sign, so minus minus is going to become plus, so it's going to be x, okay? And then because you see a and a here, and because you know the splitting rule for definite integrals, if you have the definite integral function from, let's say, p to r, then this definite integral can be written as the definite integral from p to q plus the definite integral from q to r. So this equals to this equals this integral from x to x plus h of f of t dt divided by h. Now, this quantity over here is the average value of big F on the interval x, x plus h, and equals and is equal to, remember the mean value theorem for integrals. By mean value theorem for integrals, this is equal to f of c for some c between x and x plus h. Okay, so the mean value theorem of the mean value theorem for integrals tells you the following. If you compute the average value of a function over a closed interval, then there is a point in that closed interval which achieves that average value. And what's the, like, how do you find the average value of a function over an interval? You just take the definite integral of the function over that interval and you divide it by the length. So this is the average value of f over the interval x, x plus h. And by mean value theorem for integrals, this is equal to f of c for some c between x and x plus h. Now, clearly, this number c will change because I'm taking the limit, so h is changing. So this thing actually depends on h. Okay? Nevertheless, it's always between x and x plus h. Now, as h goes to 0, what happens? As h goes to 0, x plus h goes to x. And c is in between these, which means that the c of h goes to x. Okay? So as h goes to x, this guy goes to, sorry, as h goes to 0, this guy goes to x. Okay? And this is a continuous function. If these numbers are approaching to x, and if I'm taking the limit of the values of, if I'm taking the limit of the value of these of this function at these points, then by continuity, this should be f of the limit of these ch's. Okay, and that will be okay, because f is continuous, I can just put it inside like this. So as h goes to 0, because ch's are between x and x plus h, they're going to go to x as well. So this, you're going to get f of x. So what have we proven? We've proven that the derivative of big F is small f, and that proves a part 1 of fundamental theorem of calculus. Okay. Now let me prove part 2. Let me prove part 2. Okay. Let G be any antiderivative of little f on the interval I. Then since this function big F is also an antiderivative of little f on I, we get that two antiderivatives differ by a constant, right, on an interval. I have a fixed interval here, I. So we get that a big G of x minus big G of f, these differ by a constant. Let's call this C for some C, okay? And let me actually write down the definition of. No. For some C. Now I'm gonna plugging in x equals a gives. When I plug in a, I'm gonna get g of a minus f of a equals c, but f of a is equal to 0 because integral of any function from a to a is 0. So I have that c is a g of a. Thus, we get that. Now, I'm gonna put f to the right hand side and a c on the left hand side. So I'm gonna get this. So put f over here, put c over here. You're gonna get that big G of x minus c is equal to big of x. Now we plug in x equals b and get that a f of b. Now f of b is equal to the definite integral of the left from a to b, and g of b is, well, it's g of b, and c is g of a. So maybe I should just write it over here. So I get that the definite integral of the left from a to b is g of b minus g of a, where g is an antiderivative for little f. Okay, and that's it. This is the proof of the fundamental theorem of calculus. As you can see, we proved the second part using the first part, and we proved the first part using the mean value theorem for integrals. And how did we prove the mean value theorem for integrals? Using the intermediate value theorem. And so everything goes back to intermediate value theorem. And how did we prove intermediate value theorem? Well, we didn't, because in order for me to be able to do that, I need to actually talk about the construction of real numbers, which is beyond the scope of this course. Okay, so we took the intermediate value theorem for granted, but if you learn some very basic topology and learn about the construction of real numbers, that's not that difficult to prove. Anyway, that's that. Now, some notation. Given a function, when I write this is called the evaluation symbol. That means the following. You're going to take your f, evaluate at the upper limit, and evaluate it at the lower limit, and then you're going to subtract this, okay? So we're introducing this notation because, as you can see, we're gonna like the fundamental of calculus tells us that if we're computing a definite integral, we're gonna like see this. And this also explains why we called the class of antiderivatives of a function the indefinite integral of that function. As you can see, the fundamental term of calculus tells you that this is a big g of x, evaluated at a and b. But what is big G of x? It's an antiderivative. What? Well, in general, we denoted the general antiderivative of f like this. Like this is like the class of all functions. So, okay, I'm just gonna write this down and hope that it will make sense to you. This is why we use this as we use this notation for antiderivatives, because fundamental theorem of calculus tells us that pick any function in here, evaluate that a and b, and subtract. That gives you the definite integral. Okay, this is the motivation behind that not a b. This is the motivation behind that notation. I'm not gonna write that down. That's not completely correct. Okay, so that's that. Now let's see this in a action. Over the next couple videos, we're going to learn integration techniques. We're going to be computing definite and indefinite integrals over and over again. So in this video, I'm just going to solve a couple basic questions to illustrate the fundamental theorem of calculus. Okay, more complicated integration questions will come later. So I'm planning to solve like I guess 5 or 6 questions. Oh, but before that, I should talk about something else. So let's just say warning. The assumption that f is continuous in the statement of fundamental theorem of calculus, people usually abbreviate it like this, FTC, is crucial. Now, if you look at the statement, I assumed something. I assumed that this function is continuous. And that assumption is actually crucial. Like it's important. Why? Take this function. Take this function. Do I want to do that? Sure. Yeah. Yeah. F of x is equal to 1 if x is between 0 and 1, and it's equal to 2 if x is between 1 and 2. So here is how f looks like. And this is 2, this is 1, this is 1, this is 2. Okay? Now, let me compute this function, which I'm going to name big F, which we named big F in the statement. This is the definite integral of f from 0 to x. Okay? Okay, just so you don't... that's fine. That's fine. Okay. I'm going to do something. I'm going to pretend that this function goes to the left, because in the statement I said that a is inside this interval, but then you're going to object to me 0 is not inside the interval 0, 2, blah, blah. So I'm just going to pretend that my function is defined. It's defined for all x like this. Okay. Oops. Why is it erasing the whole thing? I don't want to erase. I don't want to erase the whole thing. Okay. So let me choose my a as a 0 and write this function down. A big F of x is the integral of a little f from 0 to x. Now, if you try to compute this on the interval, let's say 0, 2, what's going to happen is this. Up to 1, you are going to get a x. Okay? Because if you pick any point here x, then this area, this signed area is going to be x. Okay? And for points bigger than 1, what's going to happen is it's going to be 1 plus 2x minus 1. Okay? The reason is, okay, I'm sorry for this. The reason is if you pick an x here, I don't know why I have this. If you pick an x here, then what's the area of this region? This part is this little square is area 1. This rectangle has area 2 times x minus 1. So in total, you're going to get that. Okay. So let me undo all this. Okay. Now, as you can see, I mean, you can easily see that when you plot the graph of this function, this is a y equals f of x. And let me also plot this one. This function, it looks like this. And then at 1, it's going to be like that. This is going to be the graph of y equals a big f of x. Okay. This is 1. This is 1. This part has slope 1. This line has slope 2. Okay. Now, the derivative of f at 1 does not exist. Okay. So is not equal to f of 1, which is 2. So the fundamental theorem of calculus tells you that the derivative of this function, okay, so this is a big F. The fundamental of calculus tells you that the derivative of this big F is small f if little f is continuous on your interval. My function f here is not continuous at 1. I mean, it's continuous elsewhere, but at 1 it's not continuous. So if I try to apply the fundamental theorem of calculus, it's gonna fail. Like it's not gonna give. It's gonna tell me something wrong, because if I were to apply the fundamental theorem of calculus to this without checking continuity, I should have that this equality holds, but the derivative of big F at 1 does not exist. Whereas the derivative of f of 1, well, it exists. It's the same. Okay. So the point is, derivative of this function at 1 is not equal to f of 1. So as you can see, I can't apply fundamental theorem of calculus here because my little f is not continuous. Okay. Also, here's another example which tells you that you can also you can't also apply the second part. So this was for the first part. Maybe I should just put here bullet point. Here's another example. Okay, consider the function defined as follows. So I have, no, I don't, that I this. I have the function f of x, which is defined as follows. It's 1 over x squared if x is not 0, and if x is 0, it is a 0. If you plot this, you'll see that your function looks like this, and you have an asymptote, a vertical asymptote at a x equals 0. Okay. Now, if you try to compute the function a minus 1 over x is an antiderivative of 1 over x on the interval 0 to infinity and minus infinity to 0. Okay? But yeah, that's that. But we have a problem at 0. Minus 1 over x is not defined. And even if I try to write down a function like g of x, which is going to behave like minus 1 over x at points other than 0, and at 0, maybe I just defined it at 0, it's not going to be an antiderivative of this at 0, okay? So you can't find an antiderivative of this function on an interval which contains the point 0, but you can find an antiderivative of this function on these intervals, okay? 0 to infinity and minus infinity to 0. Anyway, the point is this. We do not have that. We do not have, well, maybe I should just write that down. If you try to apply the second part of fundamental theorem of calculus to this, you would get that like this integral of this function from minus 1 to 1 is equal to minus 1 over x, evaluate from minus 1 to 1. So I just plug in 1 and I plug in minus 1 and subtract these. So what do you get? Minus 1 minus 1, you get minus 2. Well, do you believe that this area under the curve is like this? Do you believe that this region under the graph of this function over the interval minus 1 to 1 has area 2, minus 2? No, this is clearly not true, okay? This is not true. And the reason that we can't apply the fundamental theorem of calculus is, well, first of all, there are a couple of reasons that we can't apply it. First of all, this function is not continuous. And the second is, in the statement of fundamental theorem of calculus, I'm saying that this is an antiderivative over the whole interval that I'm working with. Well, this function that I wrote here is not an antiderivative for this function f. On the interval minus 1 to 1 because I have a problem at 0, okay? So this is why you can't actually, you can't do that. So that's that. Okay, maybe this example, I could have actually skipped this. So that's that. Now let me solve a couple of examples, okay? Where are my examples? I'm gonna solve some basic examples, okay? But do not like just based on these examples, do not fall into thinking that all my examples in future are going to be easy. This specific lecture is not about integration techniques or how to integrate. This is about fundamental term of calculus. So I'm just gonna keep my integrants basic so that I can integrate them very quickly. Find the area. Find the area of the region bounded by y equals 1 over 1 plus x squared, x equals -1, x equals 1, and y equals 0. Okay. So we're supposed to find the area of a region. Which region? The region bounded by the curves. Okay, I have 4 curves. The first one is y equals 1 over 1 plus x squared. So this is the graph of the function f of x equals 1 over 1 plus x squared, and it's going to look like that. Okay, if you actually plot it, you'll see that it roughly looks like this. And y equals 0 is the x-axis, and x equals -1 is over here, and x equals 1 is over here. So this is my region. I want to find the area of this. Now, so let me name this R. You can't see it. So let's name this region R. So the area of R is, by the geometric interpretation of integral, it's supposed to be the integral of this function from -1 to 1. Okay? Now, how do you find this? First, you can just go back to the definition, pick a partition, compute the upper and lower Riemanns, and then try to take the limit of those Riemann sums over certain partitions that you're going to choose. And if you're lucky, you'll get the same limit, but it's going to be terrible if you try to do it with this function. Okay, you won't be able to get it. Or you can use the fundamental term of calculus and say the following: any antiderivative of this function is arctangent of x, as we have seen at the beginning. Which means that by fundamental term of calculus part 2, in order to compute this integral, I should just take this antiderivative and evaluate it from -1 to 1, meaning that I'm just going to evaluate that 1 first, and then I'm going to evaluate that -1, and then this is going to give me arctangent of 1 is pi over 4, arctangent of -1 is minus a pi over 4, so I'm going to get pi over 2. So over here, I'm using fundamental term of calculus part 2. Okay? So that's that. A very basic definite integral computation. Let's do another one. Find the average value of the function f of x equals e to the power x plus sine of x over the interval 0 pi. Okay? So how do we compute the average value of a function over an interval? So the average value of f of x over 0 pi is by definition, this is the integral of this function from 0 to pi divided by the length of this interval. So I need to compute the definite integral of e to the power x plus sine x from 0 to pi and divide this by pi. Again, if you try to apply the Riemann-Sum definition of the definite integral, it's going to be a mess. You won't be able to get this. But if you try to apply the fundamental theorem of calculus, it's going to work out fine. In order to apply the fundamental theorem of calculus, part 2, what do I need to do? I need to find an antiderivative of this. Well, I know that the antiderivative of e to the power x is itself, okay? I'm just going to pretend that that was there all along, okay? So, and an antiderivative for sine is minus cosine. So an antiderivative for the sum is e to the power x minus cosine of x. Okay, this is an antiderivative for this, because when you take the derivative of this, you can get e to the power x plus sine of x. And then you're going to evaluate this from 0 to pi. So you're going to get e to the pi minus cosine pi minus e to the power 0 minus 0 divided by pi. And this is going to give you e to the power pi. Cosine pi is minus 1, so it's going to be plus 1 minus 1 divided by pi. So it's e to the power pi divided by pi. Okay? So that's that. Again, a very simple definite integral computation where we used a fundamental theorem of calculus part 2. Okay. Okay, now let's see fundamental theorem of calculus part 1 in action. Example. Find the inflection points of the function big f of x equals integral of e to the t squared dt from 0 to x. Okay. So, I need to find the inflection points of a function. What do I need to do? I need to find the second derivative. Okay? So in order to do that, I need to find first derivative. But before that, I need to look at my function. What is my function? My function is defined as a definite integral. Big F of x is integral from 0 to x of e to the power t squared dt. Now, what you can try to do is, because in the previous two questions we were able to use fundamental part 2 to compute a definite integral, you can try to do that. But you will fail because you won't be able to find an antiderivative for e to the power t squared. And it's not because I haven't taught you yet. Even with the integration techniques that you're going to learn, you won't be able to express you will not be able to express an indefinite integral an antiderivative of this function in terms of the elementary functions that we've been using. So the point is, I can't write out f explicitly in terms of elementary functions, but I don't need to, because I don't need f. I need its second derivative. So let me take, and I know something about derivatives of definite integrals. What do I mean by derivatives of definite integrals? Well, you know what I mean. I know the first part of the fundamental theorem of calculus. Okay. And by the first part of the fundamental theorem of calculus, we have that the derivative of big F is e to the power x squared. Okay. Now, the first part of fundamental theorem of calculus tells you that if you have a constant here, it, by the way, it is imperative that this is a constant, and it's at the bottom. It's not the upper limit, it's the lower limit. If you have a constant here, and if you have x here, then the derivative of the function defined by this definite integral is this integrand. That's it. So this is the derivative of big F is e to the power x squared, and that's just it. So I found the derivative of big F without having a formula which having a formula for big F. Okay. Now I'm going to find a second derivative. So its second derivative by chain rule is, this is composition of x squared with the exponential function. So I have my outer function is the exponential function. So how do I take the derivative of this? Derivative of the exponential function, which is itself, is the exponential function, and I leave the input fixed, and I multiply this with derivative of inside, which is 2x. So I have that. So if you do this table that we've been doing, if you set this to 0, if you set the second derivative to 0, you'll get that there's only one point which makes that happen, and that's 0. So I have a potential inflection point. At the moment, I do not know whether this is an inflection point or not, but if you actually plug this into the second derivative, like if you just plug in numbers from here into the second derivative, you'll see that this first term is always positive because it's e to the power something, so this is always positive. And if I plug in a negative x, it's going to be negative, and it's going to be positive. So my function is concave down here, concave up here. So this is an inflection point. So thus f has an inflection point at x equals 0. Okay, so I get an inflection point. Okay. Now, let me solve 3 more questions where I do a similar thing and differentiate a function which is defined in terms of a definite integral. Example. The second part of fundamental theorem of calculus, we're going to be using that over and over again to compute definite integrals. So like you're going to see that a lot. The first part, unfortunately, you don't really use that a lot unless you end up having to differentiate functions which are defined in terms of definite integrals. Okay, so I'm just going to devote the rest of this lecture to the first part. Okay, my questions are going to be about the first part of fundamental theorem of calculus. So example, find d over dx, and let's put I'm gonna do it like this. Integral from sine x to 1 cosine t dt. Okay. So find this derivative. Pretend that for some reason that I can't think of right now, you ended up having to differentiate such a function. So what do you do? Now you're going to use fundamental theorem of calculus, the first part, but you have to be careful. In order to apply the first part, you have to have a very special setting. You should have a function which is defined like this. It's a definite integral from a constant to x of some continuous function. Well, my function is continuous here. There's no problem with that. But the problem is this function, if I think of this as my f of x, this function is not like the definite integral. Defining this function is not from a constant to x, it's from sine x to 1. So I have to be careful. So what am I going to do? I'm just going to call this function a, yeah, that's fine. What I'm going to do is I'm going to first flip these bounds, okay, by plugging in by putting a minus sign. I know that by properties of definite integral, I can just interchange these upper and lower bounds if I put a minus sign in front, okay? So I have that. Okay. Now this is closer to the statement that I saw in the theorem, in the fundamental theorem, but it's not still the same. So I wanted to have a definite, like I need to, in order to apply the first part, I need to have a definite integral from a constant to x. Now I changed the upper and lower bounds, so my definite integral now has a constant as its lower bound, but its upper bound is not x, it is sine of x. What are you going to do in this case? Now I am going to show you a trick. Let a big f of x be the following function. Integral of cosine t dt from 1 to x, not 1 to sine of x, 1 to x. Then, by the fundamental theorem of calculus, part 1, you know that the derivative of big F is its cosine of x, okay? So if I had this scenario, if it were the case that my upper bound is x instead of sine of x, I would have that the derivative of this function is cosine of x by the first part of fundamental theorem of calculus. That would be it. Okay. But I didn't have that. Yet this will be very useful, this f. You see, the function I see here, this is not f of x, but this is f of sine of x. Which means that if I differentiate this, you see I have a minus sign in front. If I differentiate this, I'm going to get that. By chain rule, okay, this is f of sine of x. F is differentiable by fundamental theorem of sine is differentiable. So I'm going to use the chain rule. I have two functions. So what do? I differentiate the outer function first. I leave the input fixed. And then I differentiate, I multiply this with derivative of inside, which is cosine of x. Maybe I should just write it as sine x prime. Now, this observation here, this observation that I made, it tells me what this term is. F prime of x is cosine of x, so f prime of sine of x is cosine of x, and derivative of sine is cosine, so I have that. So over here, let me put it over there, and let me rewrite this. This is f of sine of x. Over here, I'm using this observation. Okay. Now, if you just watch random YouTube videos, like they're gonna teach you this as follows. When you see something like this, here is the algorithm. You just plug in this upper bound instead of t here, and then multiply the result with the derivative of this upper bound, and that would be it. Well, it is the case here, as you can see. But this is the proper way of doing that. I mean, this what I showed you here is the reason that that algorithm would work. Okay. So that's that. Now let me solve another question like this. I'm not going to completely solve this, but I am going to do half of the solution and leave the other part to you. Let's say that I want to find the derivative of the following function, which is defined in terms of in terms of a definite integral. Derivative of integral of square root 1 plus ln of t dt from x squared to x to the power 4. So what do I do? Again, just from the structure of the question, you'll see that we have to apply fundamental theorem. But again, we can't directly apply it because here in order to apply the fundamental theorem, the function which is defined in terms of an indefinite integral should look like this. It's the indefinite integral of some continuous function from a constant to x. Well, over here I don't have a constant and I don't have x. So what am I going to do? Here's what you can do in this case. Here's a trick. I am going to separate. I'm going to split this definite integral. I'm going to write it as integral of this function blah blah from x squared to 1, and let's go to 2 so that everything stays defined. Wait, what? This is, I want that. Nah. These can be, I see. Let's put +1 here so that everything stays positive. Okay, let's put +1. Otherwise, if x squared and x to the power 4, if they're both less than 1, this can be negative, which is going to make the inside of square root negative. So that may not be defined. So let's add +1 over there, so that this definite integral is now, it makes sense. Anyway, I mean, it's not going to change anything. This is not going to change the trick that I'm going to show you. So I'm going to split this integral like that. Integral from x squared plus 1 to 2, and from 2 to x to the power 4 plus 1. And then I'm going to put a minus sign and flip this like that. And now I'm going to do the exact same trick, okay, that I did before. I see an integral here, a definite integral defining a function. The lower bound is a constant. The upper bound is not x, but it's a function of x. So I'm going to do the exact same thing here and call this integral f of x 1 plus ln of t dt. So I will get that f prime of x is square root 1 plus ln t, and then by the fundamental theorem of calculus, this is minus f of x squared plus 1 plus f of x to the power 4 plus 1, and then by chain rule I'm going to have minus f prime of x squared plus 1 times 2x, derivative of inside by chain rule. And if you differentiate this by chain rule, what you're going to get is derivative of the outside function. You leave the input fixed times, you multiply this with the derivative of inside, so you're going to get that. Now I'm using the fact that f prime of x is square root 1 plus ln x. Okay, I'm going to pretend that those little mistakes never happened. So what I'm going to get is minus a square root 1 plus ln 1 plus x squared times 2x plus a square root 1 plus ln x to the power 4 plus 1 times 4x cubed. And that's it. This is a derivative. Okay? So that's that. And let me solve one more question where we're going to see the first part of fundamental theorem of calculus in action. Find the limit of this quotient. The numerator is integral of sine t to the power 4 from 0 to x. The denominator is integral of cosine t squared minus 1 from 0 to x. Okay? So, how would you I don't want to write down the exact same thing over and over again. Yes. How would you find this limit? Think of this numerator as your f of x, think of this denominator as your g of x, okay? How would you find this limit? Well, f and g are continuous. F and g are differentiable functions by fundamental theorem of calculus, so they're continuous, so I would just try to plug in the value. The problem is, if you try to plug in a 0 for x, you're going to get 0 over 0, okay? So you're going to get 0 over 0. So if you try to plug in x equals 0 in numerator and denominator, you're going to get 0 over 0, so you can apply L'Hopital's rule, okay? Because these functions, like think of this as your f of x, think of this as your g of x. These are differentiable functions, so you can apply L'Hopital's rule. And then what's going to happen is if you apply L'Hopital's rule, you're like you need to have your f prime divided by g prime, but this is by fundamental theorem of calculus. This is by fundamental theorem of calculus equal to sine x to the power 4 divided by cosine x squared minus 1. So you have that. And now we get a simple limit question, okay? This has nothing to do with integrals now. Let's try to evaluate this limit. Plug in 0, you're going to get 0 over 0, so I'm going to apply L'Hopital's rule once more. And then this is going to give me, if you apply L'Hopital's rule once more, you're going to get a, let me write it over here. Derivative of top is cosine x to the power 4 times 4x cubed. By chain rule, and derivative of the bottom is derivative of cosine is minus sine, and I leave the input fixed, and I multiply this with 2x, and derivative of 1 is 0, so I have that. Now, I'm going to do some cancellations here, and I am going to rewrite this as follows. I'm just going to put this minus in front, so I have cosine x to the power 4 times, I have a, okay, I'm gonna write this a x squared as 1 over 1 over x squared because, well, you see why in a second, and I'm gonna leave that too. So after when you do the cancellation, if you just play with this expression, you're gonna get that it's equal to that minus cosine x to the power 4 times 2 divided by sine x squared divided by x squared. Now, why did I write it like this? because you know that when x goes to 0, x squared goes to 0. So you have sine of t divided by t here, t goes to 0, so this is going to go to 1. Okay, it's going to go to 1 as limit of sine t divided by t when t goes to 0 is 1. And now this top part, this goes to 1. So this limit will be minus 2. Okay? So my original limit is minus 2. So that's that. And this is the end of our lecture today. So what have we learned? Let's go over what we did today very quickly. We learned about the antiderivatives, okay, the notion of indefinite integral, and then I listed some very basic indefinite integrals, and then we stated the fundamental theorem of calculus, we proved it, and afterwards I showed you why the continuity assumption is necessary in the statement of fundamental theorem of calculus because of this example, and I also uh, wrote another example which shows you that without checking points which can create you problems, like maybe this function is an antiderivative of this function except at a certain point, and that point is in the domain of your integration, so on. If you simply blindly try to apply fundamental theorem of calculus part 2 to compute definite integrals like this one, like trying to integrate 1 over x squared from minus 1 to 1, if you blindly apply fundamental of calculus part 2, you're going to get wrong results. So this shows you that. And then afterwards, we solved a couple questions in which we applied fundamental theorem of calculus, a very basic area question where we found the area of a region bounded by 4 curves, and this region turned out to be the region between the graph of 1 over 1 plus x squared and the x-axis between minus 1 and 1. So the area of that region can be computed by a definite integral, but that definite integral can't be computed via Riemann sums. It's going to be too difficult, so we use fundamental theorem. In the other question, we found the average value of a function over an interval. By definition, the average value of a function over an interval requires you to compute a definite integral, and we computed that using fundamental theorem of calculus part 2. And then in the other remaining questions, we use like those were out fundamental theorem of calculus part 1. We in the other questions we need to differentiate a function which is defined in terms of a definite integral. Okay. So in the first part we had this function. In the first question we had this function f(x) integral from 0 to x e to the t squared dt, and we need to find the inflection points of this, for which we need to compute the second derivative. And for the other two questions, okay, so I'm gonna say thank you, assuming that some of you said bless you, although some of you may have said like die rotten hell because you hate calculus. I hope that's not the case. Anyway, in the last two questions, we need to differentiate again functions that are defined in terms of definite integrals, but their forms did not completely align with what we have in fundamental theorem of calculus. So we did these tricks to be able to apply the fundamental theorem of calculus, and then it worked out. And in the last one, in the last question, I just computed a limit where I computed the limit of a quotient where my numerator and denominator are functions that are defined in terms of a definite integrals, and we need to, like, we saw that when we try to plug in the point, we get 0 over 0, so we need to apply L'Hopital's rule. But in order to actually differentiate top and bottom separately, we need to use fundamental theorem of calculus. That's that. And that's it. That's the end of today's lecture. Now, for the next couple videos, we're going to learn about integration techniques, how to integrate certain elementary functions and their combinations. We're going to start with the substitution method, and stay safe and expect more videos.